Okay, so we are going to review integration techniques up to this point. I've put air quotes around basic because I think some of these are kind of hard. Also, just FYI, I'm a little stuffy. I'm getting over a cold, so I apologize in advance for that. But let's get to it. So first, let's talk about just your what should be integration basics, i.e., formulas that we have for integration. Now, if you're in my class, I do want you to actually write these down. And even if you're not in my class, so this is a pretty exhaustive list. And I think the best way to remember it would be to actually just force yourself to write these down. You're more likely to remember all of these if you write them down. Some you might know off the top of your head, some you might not. So pause the video if you want to write these down. There are a couple that I would like to just highlight also. Because I think that even though I've put them down as basic, they might not be obvious. So like tangent and cotangent. So these, and also secant and cosecant. All of these can be found using substitution. I'm not going to do that in this video. That I have other videos where I show how to do that. But the interesting thing about these integrals, I just want to state, is that there's actually more than one way to write them. So if you didn't write this as secant x, you could also rewrite this as the natural log of, say, like 1 over cosine x. So some of these, depending on like how you integrate like these four, you might get like a slightly different formula, but they would still be equivalent to one another. So that's another one of those places where it's like, is it basic? I mean, it's a formula that you should technically know, but I don't know that it's necessarily totally basic. We've got sinh and cosh, and then we've got these formulas here, which I think are kind of tricky little devils to remember. But I will say this much. So in probably just about any Calc 2 class that you would be in, I think most professors would expect that you know all of these. And if you are in my class, I do expect that like this is like the base level that you're supposed to know, which is why I call it the basics. But that doesn't make them basic, right? So there's a kind of a distinction in there. So hopefully you've written these all down. And so these are just like freebies that we're going to call on at any time. All right, so now let's talk about some more creative ways to integrate. And these, I don't know that I call this basic, but a lot of books consider it basic. So I'm going to walk through just some strategies that you can use with integration. So the first is using completing the square with substitution. So it's pretty, like there's some clear tricks or clear reasons why you might want to use this. So here's this first integral. And what I would recommend is that you take a second to see how you would just integrate it off the top of your head. I think that this will make a lot more sense if you actually try to integrate it on your own for a minute and then hit play. So the thing that I notice with this is that there's like no good substitution here, right? And you might even think like, oh, I'll be clever, I'll factor out the x. But like factoring out the x still won't really like help anything necessarily. So like this is one where pretty quickly you hit a wall on it, okay? And so when this happens, then you have to get a little bit clever in like how can we actually use substitution. And so one way that you can do that is by completing the square. So to do that, what I'm going to do is first I'm going to just factor, so I'm going to rewrite this as negative x squared plus 2x, and I'm going to factor out the negative because that's just usually preferable when we complete the square. Now, to complete the square, the way that that works is that whatever number is attached to the x, that becomes our b, and then this is just what you do to complete the square if you forgot how this works. So you take half of that and then you square it. So this is just boom, boom, boom. That's how you complete the square. And from there, now what we're going to do is we're going to take this 1 and we're going to put it back into the problem. So what I want to do is I want to rewrite this as this negative x squared minus 2x plus 1. Now, I can't just go randomly changing the problem value willy-nilly, okay? Like, we are not in the lawless West, okay? Like, so if I'm going to do that, I have to keep everything the same. So what I want to do then is I want to write a number out here that will bring everything back to balance. So specifically, this negative 1, remember, it will get bounced off of this negative here. So what I have done, do you see this? I really put -1 into this problem because this 1 bounces off this negative. So this amounts to -1. So to offset that, what I'm going to do is that I'm going to add a 1 out here. And so now what I can do is I can rewrite this as negative x minus 1 squared plus 1. Okay, so let's see what that buys us. So now I'm going to rewrite this problem as the square root for 1 minus x minus 1 squared. Okay, and so now notice that if I try to use substitution, so if I set my u equal to x minus 1, then my du will equal dx. So this feels like I have a lot more traction than what I had previously. So let me make a little space here. And so now I can rewrite this. So let me change my color. So this will be du over the square root of 1 minus u squared. And so then what does that look like? Well, then that looks like inverse sine, right? So going back to our little list of charts here, right? So 1 squared minus x squared. So this can be written as this. And so now where I have the x, I will now make that replacement. So this will become inverse sine of x minus 1 plus c. Okay, so there's also some like creative multiplication that you can do sometimes to ultimately do some substitution. So looking at this problem, so we have a very similar issue like the last one, right? So as you kind of go through like your Rolodex of thoughts of how can I use substitution on this, like u to the e to the 2x is not going to work because then my du will be 2e to the 2x, and that is not anywhere to be found, so that's not going to work. And then just making this e to the 2x won't work because I don't have another e to the x in the problem. So like, you know that you have to be clever if you're kind of out of ideas for substitution. So let me get rid of all this. Okay, so now what other ideas could we throw at this? Well, one thing that we can think about is, so this is something squared minus 1, right? So one thing that you can do sometimes is you can look at this little handy dandy list and you can kind of think about, or you can look and see if there's like maybe a format that we could leverage so that we could actually integrate this darn thing. And so one thing that I notice is, so I do have this like square root. So I do notice like this form here could be sort of similar, but my problem starts with e to the x, not a, right? So a needs to be a constant. So I don't start with a constant, right? I start with e to the x. So this one looked maybe like it was promising, but it's not going to work. Not going to work. This one, so this one starts with x squared minus a squared, but it's got an x out here. So we'll just think about that. And then this one here has an x squared minus an a squared. So maybe we could do something with that. So I have really these two forms here. So the question is then, is there some way that I can cleverly manipulate my integral so that I can leverage one of these with substitution? Okay, well, there actually is a more obvious answer to this. So this form here is not going to work because ultimately I have this thing squared. There is that e to the x is just kind of a problem. So what we're going to do is, this is actually going to be kind of the target form that we're using. So I'm just now going to show you the trick because I probably have just overwhelmed the explanation at this point. If I did, sorry, but just keep going on this ride with me. Okay, so here's what we're going to try to do. So a lot of times when you have e to the x's in a problem, a lot of times it can just work out to multiply by e to the x over e to the x. And so you just have to kind of see what's going to happen. Now, multiplying by this will not change the value of anything, right? So there's that. So if I do that, this becomes e to the x dx over e to the x times the square root of e to the 2x minus 1. But now, look what happens if I try to do my substitution. So now I have my u can just be e to the x, and my du can be e to the x dx. So what this allows me now is to take this entire top part and turn it into a du. So this already feels like I'm getting way more traction than what I had in the previous problem. So this e to the x du now, e to the x dx just becomes du. And then in the denominator, I have u times the square root of u squared minus 1. And like I said, this is why you kind of want to look at those problems or look at your formulas sometimes. So now this mimics this format here, right? So now we're actually good to go and we can finish this thing. So sometimes you can get inspiration by looking at some of the formulas if you're totally stuck. And a lot of times with e to the x's, you can just try multiplying by e to the x over e to the x. Maybe it will do something for you, maybe it won't. But anyways, okay, so this is going to become inverse secant u plus c. So then this is going to ultimately be inverse secant e to the x plus c. And bada bing, bada boom, we're ready to go. So now let's talk about multiplying by the conjugate. Okay, so this is another trick. So I have dx over 1 minus secant squared x. So in this case, like again, you just hit a brick wall right away, right? There's no way to substitute with this. So sometimes if you have an expression that you could easily multiply by the conjugate by, sometimes this works. There's no like, at this point where you are kind of in math, like you kind of just have to see what you've got and go from there. So it's not like this trick will work every single time, but a lot of times it will work. And so you just have to start learning like how to make good guesses. So now if I go ahead and I FOIL everything, so this is going to give me 1 minus secant squared x in the denominator. So now that I have this, so what I notice I could do is I could separate this into two separate fractions now. So this will become 1 over 1 minus secant squared x, and this will be secant x over 1 minus secant squared x. And what else do you notice that we could do? Well, the other thing that I know is that 1 minus secant squared x is somewhat related to a particular identity. So that identity is 1 plus tangent squared theta equals secant squared theta. So if I manipulate this, so what I will actually get is that, what I will get is that negative tangent squared theta equals 1 minus secant squared theta. So this identity here I can actually use with this problem. So everything now can be rewritten as 1 over negative tangent squared x minus secant x over negative, this should have been plus, and then tangent squared x. Okay, and so now I think we're making some progress here. So now let's make some space. Okay, so from here, now what I can do is I can rewrite this 1 over negative tangent squared. This can be rewritten as negative cotangent squared x. And then for this other one, so let's see, how can I write this? So secant x is really 1 over cosine x. And then this, so being over tangent squared x, so tangent is sine over cosine, but since it's in the denominator, this is cosine squared x over sine squared x. And so then you can see that this cosine will drop out. So, okay, so now what am I left with? So I'm left with negative cotangent squared x minus cosine x. Let's see, actually I'm going to break this into two separate integrals now. So let's call this negative cotangent squared x dx, and then minus cosine x sine squared x dx. Okay, cool. Okay, so now I'll use my own brand name here. Let's divide and conquer. So for this cotangent squared x, so this I cannot integrate, right? What I can integrate is I can integrate cosecant squared x, but I can totally relate negative cotangent squared x to cosecant squared x. So using a similar property from before, so this negative cotangent squared x can be rewritten as 1 minus cosecant squared x. So, okay, so this one I can now integrate. And now for this other one, so now we're going to have to use some substitution to get the job done. Okay, so let me make some space. Okay, so now, let's see, let's just integrate this part here. So this will be x plus cotangent x. So that part's done. And for this other part, so my u will be sine x, so then my du will be cosine x dx. So let's see, I'll evaluate this integral right here. So this becomes 1 over u squared. Let's actually write that as u to the negative second du. So then that is going to equal u to the negative first, and then I can put just a minus in front here. So when all is said and done, so this is x plus cotangent x. And then here, so this minus and this minus will cancel out. So this becomes plus sine x to the negative first. And what is sine x to the negative first? So that's 1 over sine x. And what is 1 over sine x? 1 over sine x is cosecant x plus c. So there's our final answer finally. Okay, so going back to creative multiplication, so another one that I just want to throw out here. So I've got 1 over e to the x plus e to the negative x. So I've already given you some hints on this. I would strongly recommend that you try this one just totally on your own for a moment and see if you can figure it out, and then hit play when you're ready. So for this one, so again, this is another example of using creative multiplication, but I did talk about, like, a lot of times with e to the x, you can multiply the whole thing by e to the x over e to the x. So in this case, if I do that, sometimes it works, sometimes it doesn't. So this becomes e to the 2x, and then e to the negative x plus e to the x. So what is that going to become? That's actually just going to become e to the 0, so that will equal 1. Let me make this look a little nicer. Okay, and so then I've got all of that, and then we've got the dx. So now I can set my u equal to e to the x and my du equal to e to the x dx, so that I can rewrite this as du over u squared plus 1. And then again, if we just refer back to our handy dandy little sheet here, so that is going to coincide with inverse tangent. So this one, now that we kind of know some of our tricks here, we know how to move forward with this. So this is ultimately going to be inverse tangent e to the x plus c. So we've already seen this trick, and I think the nice thing with this topic, even though it starts basic, you kind of start to notice some of the tricks to think about. So one of the other tricks that I do just want to call out explicitly is splitting up the fraction. So this next problem is like one of those key ones where I just would want to split it up. So is it always the case that you want to split this up? No. It could work out that you don't need to, but it's something that you probably just want to explore. Because with all of these problems now, you're kind of in a situation where you just want to explore and think before you do anything else. So what I like to do is I like to break up two separate fractions like you see here. And then you have options. So for 1 over cosine squared x, so I know that that can be rewritten as secant squared x. And the integral of secant squared x is, of course, tangent, so that one is good to go. And then for this other one, so I've actually seen students do all kinds of things with these types of problems. So you could go ahead and substitute. You can also just think a little bit more about what this represents. So sine over cosine, I know, is tangent, and then 1 over the other cosine. So 1 sine over 1 cosine will give you the tangent, and then 1 over the other cosine will give you secant. So you could have just plowed ahead with substitution. That would have been fine. But you can also take an extra second just to think about this, because now I don't have to use substitution, right? So now I can just go ahead and just finish it. So that's kind of cool. And so the integral of secant squared will be tangent, and then this is really secant tangent, this tangent secant, but anyways, this will be just secant x and then plus c. So that one actually, by breaking it up, became a lot easier. So anything can kind of happen with these problems. The last technique that I want to talk about is using long division. So if you are rusty on your polynomial long division, so that's going to actually bite you with integrals. So I do have a review video, just a quick review on how to use long division. So if you know that you could use a few extra examples just on long division, I strongly recommend that you check that out. But here is your classic problem that is screaming for long division. Why do I know that? Well, because the exponent on top is greater than on bottom. So when that happens, rather than breaking this up into two separate fractions, which we could also do but wouldn't help us, we should just try to simplify this fraction a little bit more and see if that makes the whole thing easier. Because you can tell by looking at this, right, like substitution isn't going to help. And really, if you break up, if you think about it and play with it for a little bit, you're going to find that also you can't easily like break this up and then use substitution. So we're going to try long division. So for my long division, so I'm going to have 4x squared, 0x, and 7. So I ask myself, how many times does 2x, or what do I multiply 2x by to get to 4x? So that would be 2x. 2x times 2x is 4x squared, but I have to multiply this 2x by this entire expression, so I also have to do 2x times 1, and 2x times 1 is 2x. And then I have to subtract all of this off. So what happens, the 4x squareds drop out, and I'm left with negative 2x. And then I can bring the negative 7 down, and now I repeat the process. So what do I have to multiply 2x by to get to negative 2x? Well, in this case, that would be just negative 1. Negative 1 times 2x is negative 2x, and negative 1 times 1 is negative 1. And then I have to subtract all of that off for my long division. So once again, these two x's are going to drop out, and then this will actually become a positive, so this will just equal negative 6. So what do I do with that negative 6? That is now a remainder, and so this is going to be a remainder, negative 6 over 2x plus 1. So I do expect that you're going to be able to bust this out. Any calculus class is going to reasonably expect that you can bust out doing these types of calculations. And so this is what I'm going to integrate now. And this is much easier to integrate than what we had before. So let's make some space. So to integrate this, so this part here I can easily integrate. So this is going to be x squared minus x. And so then for this last part here, so now we're going to have to be a little more clever. So let's see. So I'm going to have my u equal to 2x plus 1. So my du will equal 2 dx. So if I set up this integral here, I can see that, let's see this. So this 6 I can factor out a 3. And so then, all right, let me back up a little bit here. So I have 6, which could be rewritten as 3 times 2 over 2x plus 1 dx. Okay, so I bring that up because this 2 and this dx, this can all go for my du, right? So I can break up that 6 strategically, and then of course the u will go for the denominator. So I'm going to take that remaining 3, I'm just going to toss it out in front for a moment. So this becomes du now over u, so this is 3 times the natural log of 2x plus 1 when all is said and done. So my final answer is x squared minus x plus 3 times the natural log of 2x plus 1 plus c. And so that's it now for that one. That would be the final answer. Okay, so that was kind of a longer video, but hopefully now you see kind of some of the tricks that you can try. If you found that helpful, I'd love it if you hit that like button. And otherwise, I will talk to you guys in another video. Peace.